Swayam Prabha. Digital India. Educated India.
Welcome back everyone. Before this we had a discussion on experiments and we tried to understand endogeneity problems. So, what we are going to do next is to understand situations where we cannot run experiments to see if some statistical or econometric tools can come to our rescue in terms of getting the causal effect. So, we start with instrumental variables today. Let us review a bit of what we have seen so far. So, what we have discussed so far is the goal of regression analysis. The goal of regression analysis is to estimate the conditional expectation function, expectation y given x. Now, what we have over here in the very first line that you see, we have the expectation function in the mean deviation model, that is without the intercept term. So, this model actually subsumes the one with intercept, and what we are going to do is we are going to try to understand the idea of where instrumental variables or how instrumental variables can help us to retrieve the true value of beta. So, our interest as usual is the unbiased estimate of beta, which is the change in the conditional mean given an exogenous change in x. So, one of the examples that we can think of that we have discussed in the past in the effect of earnings caused by an increase in schooling attributed to exogenous reasons that are not a choice of the individuals. So, what we mean over here is basically that we are interested in the effect of education on earnings, where education is not a choice of the individual, but experimentally given or randomly given to the individual. So, in such a context where we can treat education as exogenous, we are interested in the effect of education on earnings. So, the OLS model, the regression model that we have is y equal to beta x plus u. Once again we do not have the intercept term here, because you can assume for simplicity that this model is the mean deviation model. Now, the standard regression model makes the 0 conditional mean assumption, which is expectation of u given x equal to 0. Then the only effect of x on y is essentially given by a direct effect via the term beta x, and where x and u are independent causes of y. Now, what does that mean? To graphically see what this means, let us try to understand it through a path diagram. So, what we are saying over here is we have y which is caused or affected by x, but we have other errors or other variables maybe that causes y, but these are independent causes of y where there is no connection between x and u. So, this is exactly what we mean when we say that x and u are independent causes of y. However, there may be an association between regressors and errors due to several reasons. So, one of the reasons is measurement error that we have seen partly before. The other cause could be omitted variable, again something that we have discussed in the past, and then simultaneity. We have touched upon simultaneity, we are going to have some discussion on to understand simultaneity in this context. So, let us take an intuition to understand the omitted variable idea. So, suppose a person has high level of u as a result of high unobserved ability. So, when we say unobserved ability, what we mean is that we do not observe the ability of this person, and we hence we cannot control for ability in the regression equation y equal to beta x plus u. So, we cannot explicitly control for ability, which means that ability is now part of u, which explains y, something that we just saw before, that x leads to y, u also leads to y, but then x and u are not related. X, we have a direct effect of x on y and a direct effect of u on y. And now what I am saying is that ability is part of this u over here and ability affects y. However, this raises earnings since y equal to beta x plus u, but it may also lead to higher levels of x since schooling is likely to be high for those with higher ability. So, now we are changing the path diagram, in other words, to say that x and u are actually related to each other. In other words, ability not only affects y, which is ability not only affects your earnings, but it also affects the x, which is your schooling. A more able child would be able to earn a higher wage, for instance, not because of schooling per se, but because maybe the child has higher cognitive ability, is smarter, etc. But this child, when while growing up, might also attain higher levels of schooling simply because the child is more able. So, which means now we have an association between x and u, which leads to an additional effect on y, a feedback effect. So, now there is an association between x and u, which leads to a higher impact on y. So, what are the consequences of this correlation between x and u? Now, higher levels of x have two effects on y. One is the direct effect via beta x, the second is an indirect effect via u affecting x, which in turn affects y. This is remember, as opposed to what we saw earlier, where we assume that there is no association between x and u, and in the case that there is no association between x and u, we do not have this part of the path diagram. But now when we assume an association, or when we there is a possibility of an association between x and u, what we are saying is that there is a direct effect of x on y, which is captured by beta x, but there is also an effect of u on y via x, right. So, which means that now when x increases, there is a direct effect via beta x and an indirect effect via u affecting x, which in turn affects y. Now, the goal of regression is to estimate only the first effect, which is the unbiased effect of x on y, which is captured in beta. So, another way of looking at this problem is to understand how we get to beta, or the slope of the regression line that we estimate, slope of the linear regression line, in other words, that we estimate. So, let us start with y equal to beta x plus ux. Now, we assume that u is a function of x, because in the path diagram that you saw, what we are saying is that u not only affects y directly, but it might also affect y through x, because it is associated with x. So, this idea is captured in ux, u as a function of x. Now, with total derivative, what we end up having is dy dx, which is, remember, we want this to be the slope of the linear regression line, or the OLS that we draw, that we estimate. So, this is now equivalent to beta, but now because u is a function of x, we have an additional term, which is du dx. Now, data only gives information on dy dx, obviously, because when we have information on x and y variables, all we can do is to try to draw a linear regression of x on y, and that gives us dy dx, but not necessarily beta. The only way that we can retrieve beta is when we assume that this du dx over here is equal to 0, that is when there is no association between u and x. Now, OLS estimate will instead combine these two effects, of course, and what we might have is that we have the estimate of beta, which is B OLS, as I represent here, the estimate of beta. So, the OLS estimate of beta, which is captured by B OLS, will be greater than beta when du dx is positive. That is, both effects are positive, in other words, that x affects y in a positive manner, and then u also affects y in a positive manner, and u and x are positively correlated. So, the only condition under which we can retrieve beta, the true value of beta, is where du dx equal to 0. And recall, now the analogy with the experiment, what we learned in experiments is that in experiments we try to randomly allocate observations or units of observations to treatment and control groups, so that there is no association between u and x, between the treatment allocation, what we had symbolized as d before, between the treatment allocation and u. So that this leads to what we have is the what we do not have in that case is the selection bias, which is again captured by the du dx term. So, let us take a more specific example of endogeneity in the context of policy making, suppose. So, suppose we have a cross sectional data. So, what does a cross sectional data mean? Just to review what we had discussed before, a cross sectional data where you have only one time period of various cross sectional units. It could be individuals, it could be various states of India, various districts of India, it could be various firms. So, you have different units of observation which are not related to time. So, that is when we call it a cross section. So, cross sectional regression of public health outcomes, say the proportion of population in various cities suffering from a particular childhood disease on public health expenditures per capita in each of these cities. Suppose we are interested in this question, that whether spending, which is public spending, is effective in reducing the incidence of the disease. But when we ask this question, we must also consider the possibility of reverse causality. Now, what does reverse causality mean in this context? It is a possibility that when governments or policy makers decide how much to spend in each city on public health expenditure, on public health infrastructure, that decision is also guided by the historical incidence of a particular disease in that city. Now, suppose we think of dengue outbreak. Now, when we think of dengue outbreak, obviously governments in cities where dengue outbreak has a higher incidence would end up spending more, right. So, but when you try to see the effect of expenditure on the health outcome, whether people suffer less from dengue after expenditure has increased, there is a potential confusion because expenditure is also higher in those cities where dengue outbreak is higher. So, you might end up getting a correlation in the wrong direction, where you find that cities where expenditure is higher are also cities where the incidence of the disease is higher, and you might end up inferring from that wrong correlation that higher expenditure is leading to higher incidence of the disease. So, this is exactly what we had discussed before, is the confounding effect of various types of problems like the omitted variables, like measurement error. In this case, we are talking about reverse causality. So, just to repeat, the level of expenditure is likely to be partially determined by the historical incidence of disease in each jurisdiction or city. In this context, OLS estimates of the relationship will be biased even if additional controls are added in the specification, because the case that we are discussing here is a little bit different from omitted variables, it is distinct from omitted variables. Hence, even if we control, suppose we had all or a rich set of data and we could control for these various indicators, various factors that affect both expenditure on health as well as the incidence of health, we might still end up getting a spurious correlation because of reverse causality, which is not addressed by adding more control variables. So, what do we need to do? So, what we are trying to understand here is the effect of public health expenditure on the incidence of the disease. Now, for this, because there is a potential possibility of reverse causality, that higher expenditures are made in areas where there is higher incidence of the disease, what we need to do is we need to model the public health expenditure. So, although we may have no interest in modeling public health expenditures, we must be able to specify such an equation in order to identify the relationship of interest. Now, this is very important, as you will see, because this forms the crux of the idea behind the instrumental variables. So, let us look at the history of instrumental variables a little bit, in what context did instrumental variables actually pop up, and then we discuss what instrumental variables actually are. Now, instrumental variables came up as a fix for endogenous regressors. So, the IV approach grew out of early econometric research on the problem of how to estimate the parameters in a system of linear simultaneous equations. So, the term endogenous regressors arise from simultaneous equation models, where the explanatory variable, which is the exogenous variable, is also determined in a separate equation as a part of the system. Now, look at the how to connect what we learn over here to the last point on the previous slide, that is, we need to model public health expenditures. So, what does this mean? Public health expenditure is actually an explanatory variable when we are looking at the relationship between public, or how the causal relationship from public health expenditures to the incidence of the disease. And what we are saying over here is, we, in order to understand the causal relationship from public health expenditures to the incidence of disease, what we need to know, or what we need to do, is understand that these endogenous regressors, in this case by endogenous regressor we mean the public health expenditure, arise from simultaneous equation models where it is determined in a separate equation as part of the system. So, public health expenditure itself is an outcome variable. It is not just an explanatory variable in the equation of incidence, health incidence on, or disease incidence on public health expenditure. It also appears as an outcome variable, as a dependent variable, y, in another equation, where public health expenditure depends on other variables as well, including the health incidence, right, the disease incidence. So, as it turns out, this was the context in which the need for instrumental variables was felt. So, instrumental variables shortly is in this particular context, it is essentially a variable that would affect public health expenditure when you are trying to explain public health expenditure in the simultaneous equation model, where it is an outcome in a separate equation. So, there is a variable that affects public health expenditure that shows up in the public health expenditure equation, but it will not affect the incidence of the disease itself. Okay. So, it will not show up as a significant variable in the in the model where we are trying to understand the impact of public health expenditure on the incidence of public health itself. However, while this was the context in which IV actually originated, the instrumental variable idea actually originated. Nowadays, IV does much more than allow us to consistently estimate the parameters in a system of simultaneous equations. So, what we find today is the use of IV has grown out of simultaneous equation models, and we can also use, so there is a wider application of the instrumental variable technique even in contexts when there are omitted variables, when there is measurement error and other sorts of endogeneity problem which we try to solve using instrumental variables. Now, getting back to the simultaneous equation model, because that is where IV started, the foremost example of simultaneous equation model is the supply demand framework in economics, in which price and quantity are jointly and or simultaneously determined in the market for goods and services. So, something that we have seen before. So, what we are saying over here is, suppose we want to estimate the response of market demand to exogenous changes in market prices. So, how does demand respond to prices? So, if you go back to if you remember from our very first lecture, we had discussed the a potential example from market research, where suppose Starbucks wants to come to India and set up. So, think of a time where Starbucks was not there in India and it is coming to the Indian market for the first time, and it wants to understand how to price its product in India, because pricing of course does not always depend only on the cost, but there are markups and so on. So, the idea is that if when it is trying to decide how much price to charge for a cup of coffee, it needs to understand what is the demand at a particular price. So, it needs to understand the demand elasticity of coffee. So, only if it understands the demand elasticity of coffee would it be able to find out that if a price P is set for a cup of coffee, how much demand there would be, and hence how much revenue the firm would earn, and effectively what the profit would be. So, in this context, quantity demanded clearly depends on price, but prices are not exogenously given, since they are determined in the market in part by market demand. So, this is the simultaneity problem that we are talking about, that in order to understand the effect of increasing price on market demand, we need to understand the causal relationship, the true causal relationship from price to market demand. However, when we are talking about prices, prices are not determined in some vacuum. They are not or given exogenously to let us say Starbucks. It is determined as part of this equilibrium in the which is determined in turn by the intersection of market demand and market supply. So, which means in other words that we have price as an outcome variable, as a dependent variable in another system, which is part of the simultaneous model that we are talking about over here, and price itself is determined by quantity demanded, which has been a dependent variable in the other equation, and it is in addition to quantity demanded, there are other factors that also affect prices. So, to formally understand what we are talking about over here, we go back to the supply demand framework that we have seen before. So, we have a demand equation where quantity demanded is a function of price, a negative function theoretically, and we also have price in the supply function, right, another function where we have where prices affect supply. Now, you could also think of the supply function as prices being affected by the supply, the quantity supplied. Okay. So, the inverse supply function in other words. So, assume that demand shock Ui and supply shock Vi are uncorrelated, just to make it simpler. So, at equilibrium supply equals demand. So, then what we have is we have these two equations where Yi is essentially quantity demanded in this equation and Yi is quantity supplied in this equation, and what happens in equilibrium is we set the quantity supplied equal to the quantity demanded, and as soon as we do that, what we end up having is Y in terms of all the parameters of the model, which is beta, B and alpha, and of course, Ui and Vi, the error parts, and additionally what we have is we have prices. Once again we just simultaneously solve these two equations, and we also have the prices in terms of beta, B, Ui and Vi. So, essentially what we have is a weighted average of the two parameters B and beta, which are parameters from the supply and the demand side of the market, not just B, which we are actually interested in. So, we are over here, just to repeat, we are interested, or Starbucks as a company is interested in B, which is the effect of prices on, the true effect of prices on quantity demanded. But what we see in equilibrium, what we see from data is actually the equilibrium points only, which is a weighted average of both beta and B, and not just B, which we, as a company I am interested in. So, when I regress Yi on Pi, what I get is this weighted average value of B and beta. Diagrammatically, to understand what we are talking about over here is the following. What we are trying to, or what Starbucks as a company is trying to understand is this negative relationship between price and quantity. Okay. How does quantity change? How will the quantity demanded for coffee change if I change prices? But the trouble is that the data on which we are mapping this price quantity relationship is not coming only from the demand side, it is coming from the equilibrium points, which are intersections of demand and supply. So, what we get is, for instance, we have an intersection point of D1 and S1, which is the equilibrium point in period 1, let us say. In period 2 we have another intersection which is given by D2 and S2. In period 3 we have yet another intersection which is given by D3 and S3. So, what we have is we have a simultaneous determination of price and quantity in equilibrium. We do not see price and quantity away from equilibrium on the demand function, we only observe these equilibrium points. So, what we end up getting in data, if we have suppose price and quantity demanded or price and quantity data from various periods, what we end up getting is price and quantity consumed, maybe purchased, how much coffee was purchased in equilibrium, which is basically an intersection of supply and demand in various periods of time at various prices. Now, when we try to draw a correlation among this point, we might end up with no correlation at all. But does this mean that price does not affect quantity demanded? No, because of course, these are not points on the demand function. What we are estimating as a linear relationship over here, which is a 0 relationship, are essentially the relationship between price and equilibrium quantity demanded and supplied. So, observed data on price and quantity would not lead you to a causal relationship between price and quantity demanded. So, in this context, what is instrumental variable? So, we need a method to generate only exogenous variation in price, so that once we generate an exogenous variation in price, we would know how is quantity demanded changing to that exogenous variation in price, which is not related, and this change in price is not related to quantity demanded to changes in quantity demanded itself. So, then we can say that due to a change in price from let us say 2 rupees to 3 rupees, how much does quantity demanded of coffee change, where we are sure that the quantity demanded, the change in quantity demanded itself does not have a feedback effect on the change in prices. So, again this is basically saying that we will something that will not affect quantity demanded, but will only affect prices. So, one way to think of instrumental variables in this context is to think of supply shifters that do not affect demand. So, in other words, what it means is that if you go back to the scatter plots in the previous diagram, so what we have is we have these various points which are equilibrium points, and suppose we are only talking about a specific demand curve D1, which is not changing, because now we are talking about instrumental variables or variables that affect prices, but does not affect demand. So, one such variable to think of is something that affects supply. Okay. So, suppose we start from S1 and something that shifts supply to S2 to S3 with higher values or lower values of that variable to S4. Now, as we move from S1 to S3 to S4, what changes is the supply and hence the price, because price is also a function in the supply model, is also a variable in the supply model, supply function, and as supply changes, price changes. But because this shifter that we are talking about, this variable that we are talking about does not affect demand, so demand does not change from this D1, it stays at D1. So, given this situation, given that we could come up with such a variable, a supply shifter in this context, what we are doing, notice, is we are mapping these points as supply shifts from 1 to 2 to 3 to 4, which are all points on the demand function. So, in the process what we have done is we have traced out the demand function D1 as supply moved from S1 to S2 to S3 to S4. So, this is what we just saw. So, equilibrium price and quantity when only the supply curve shifts and the demand curve does not shift. So, IV estimates the demand curve by isolating shifts in price and quantity that arise from shifts in supply. Okay. So, we can think of any supply side factor that would affect supply. So, as we move from S2, S1, S3, what we are saying over here is suppose in the context of agriculture. So, suppose there is a weather shock, whether higher rainfall leads to either higher or lower levels of agriculture, depending on whether we are talking of higher rainfall from droughts or higher rainfall from floods, and this higher rainfall does not affect quantity demand or is less likely to affect quantity demanded, but it is likely to affect the supply, because it will affect the production of crops, and hence it shifts the supply from S2 to S1, S1 to S3 and so on, but it does not affect D at all. Now, but when S shifts from S2 to S1 to S3, of course, the price will also change, because we have lower or higher supply depending on whether we are moving from S3 to S1 or S1 to S3. Now, because prices change as well as supply changes, what we can try to find out now is how does demand change in response to these changes in prices, which are not in turn caused by changes in demand, but exogenous changes in prices. So, as soon as we have exogenous changes in prices due to some other reason, which is in this case supply side, we are trying to say how much does demand change in response to these exogenous changes in prices, and then we have isolated the demand elasticity. Okay, so, Z is essentially what we symbolize IV, the instrumental variable, as, and it is a variable that shifts supply in this context, but not demand. So, in general, just to generalize what we just said in the context of supply demand framework, what we are saying is what we need is a method to generate only exogenous variation in X. What we have is that Y is a function of X in one model, but we also have X as a function of Y in another model. And what we need, because of this problem of simultaneity, we are not able to isolate the effect of X on Y. So, what we need over here is some variable or some way of generating an exogenous change in X. Now, when we are talking about exogenous shifts in X, one way to generate that is of course randomized experiments that we have seen before. So, what you could do is you could randomly allocate people or units of observations to treatment or control group. So, suppose you could randomly generate prices, for instance, in this context. So, one way is through a randomized experiment, but what we are trying to understand here is that in the absence of randomized experiment, is it possible to have an approach where we can isolate exogenous changes in X in observational data. So, a crude experimental or treatment approach is still possible using observational data, provided that there exists an instrument Z such that changes in Z are associated with changes in X, but it does not lead to a change in Y aside from the indirect route through X. So, what we are saying, in other words, so just to draw a path diagram, what we are saying now is that we have Y and then we have X causing Y, which is the direct effect of X on Y, then we have U as we had before, but now the problem is that because U and X are correlated, we have an effect of X on Y not only through X only, but also through U. Now, can we have a variable Z that affects only X? Okay. So, in this case X, remember, is the in the example that we just discussed, X is the price, Y is quantity demanded, and there are variables that where X is also determined by Y. So, there is a reverse causality here or a simultaneity, and suppose we can find a variable z that only affects x. So, in this context z is the supply shifter that only affects the prices, but does not have any effect on y. This is ruled out, but does not have any effect on y. So, this is ruled out. So, in this context, given that we have a variable z which affects x, but not y, what we can try to understand is this relationship over here, which is isolating the effect of x on y due to z. And that is the whole purpose of using an instrumental variable, because now we have been able to address this relationship between u and x not through a randomized experiment or not through driving this relationship to 0, which a randomized experiment allows us to do, but completely using a different variable that is able to bypass this relationship between x and u. So, coming back to where we were, what we are saying once again is that z is causally associated with x, but not with u. And what we are saying is, again, it is still the case that z and y will be correlated, but the only source of such correlation is the indirect path of z being correlated with x. Just recall the diagram that we just saw, the path diagram. So, the only way in which z affects y is through x, which in turn determines y. The more direct path of z being a regressor in the model for y is ruled out. In other words, z affecting y directly is ruled out. The only way that z can affect y in this case for it to be a valid instrument is through x, because only then can we say that changes in z are associated with changes in y, and that association is only due to x. And in this process we can try to find out, or we can estimate the effect, the causal effect of x on y. So, just to lay out the assumptions of instrumental variable approach. So, now that we understand the path diagram or the intuition between behind instrumental variables, what we try to do is we try to formalize them as assumptions. So, z is called an instrument or instrumental variable for x in the regression of y on beta x plus u if z is uncorrelated with u, right, because that is exactly what we saw. We do not want z to be correlated with u, because we are trying to address the correlation of u and x. We only want z to be correlated with x and nothing else over here. So, it should not have any direct effect on y. So, z is uncorrelated with u. So, correlation zu is equal to 0, which is the exogeneity assumption, and the second one is z is correlated with the regressor x. That correlation zx must not be equal to 0. So, the first one is called instrument exogeneity or the exclusion restriction. It excludes the instrument from being a regressor in the model for y. Since if instead y depended both on x and z and y is regressed on x alone, then z is being absorbed into the error where you miss out z. So, then z becomes an omitted variable actually in that regression if z was actually correlated with y directly. So, that x will then be correlated with the error. So, it again will raise an omitted variable problem if suppose z was directly correlated with y and not only through x, because in that case if z is directly correlated with y, then in this regression over here if you miss out z, then z becomes an omitted variable because it is correlated both with y and with x. So, what we want is a variable z that is correlated only with x, but not with y directly. It affects y through x. So, that once we have controlled for x in this regression, there is no need to have z in this regression anymore. It will be so that the effect of z on y follows only through x. So, that is called instrument exogeneity, that the instrument is not correlated with u and hence exogenous, or it is called the exclusion restriction because what we are saying over here is that Z is excluded from this structural model of the relationship between x and y. We do not have Z in this model and hence Z is excluded. The second condition is called the instrument relevance condition, which requires that there is some association between the instrument Z and the variable being instrumented, which is x. So, unless you have some association between x and z, if you go back to the, if we go back to the path diagram. So, we need some association between x and z, because unless there is some association between x and z, we cannot find out the path from z to x to y. So, that is the instrument relevance condition. So, revisiting the demand and supply example. So, now that we have defined an instrumental variable, a suitable instrument for price is a variable that is correlated with price, that is correlated with x, but does not directly affect the quantity demanded, which is y. So, an obvious candidate is a variable that affects market supply, since this also affects prices, but is not a direct determinant of demand. This is exactly what we saw in the supply shifter before, that we are talking about a variable that shifts the supply function, and as you shift the supply function, it does not affect the quantity demanded. So, we have an instrument Z that shifts the supply function, that affects, and hence it affects prices, but it does not affect quantity demanded directly. So, one example is a measure of favorable growing conditions if an agricultural product is being modeled. So, suppose we are, so what we had discussed before is this Starbucks coffee example, but now suppose we move to agricultural product. So, you can think of demand for anything, and the reason that we are first talking about agricultural product over here is because that this is traditionally the example in which the instrumental variable actually came up. So, an example is a measure of favorable growing conditions in an agricultural product. So, provided favorable growing conditions do not directly affect demand. So, once again, suppose we are talking about coffee beans here and not the final cup of coffee that is sold in the retail outlet. So, suppose we are interested in this log of coffee demanded, and this is the log of price of coffee, and what we are interested in is this coefficient beta, which captures the elasticity of demand for coffee. And suppose that Z, one variable that could very well serve as an instrumental variable is rainfall in coffee producing regions, because rainfall affects the crop of coffee. Another possibility is to think of a tax on coffee, okay, because once again tax affects from the supply side the prices only. Tax does not, a tax on the price of coffee, let us say something like an ad valorem tax, a supply side tax is unlikely to affect demand directly, but it is likely to affect demand only through the changes in prices, because consumers now will have to pay a different price. So, tax is another potential instrumental variable. Now, let us for the time being only consider on rainfall. So, is Z a valid instrument? So, remember, to meet the conditions for a valid instrument, an instrumental variable must meet two conditions. One is exogeneity, that is the correlation between rainfall and this U over here must be equal to 0. So, is this equal to 0? Well, possibly whether it rains in coffee producing regions should not affect the demand for coffee. The second one is the relevance condition, that is the correlation between rainfall and the price of coffee. Once again, it is possibly likely to be met, because high rainfall means that it will affect the supply of coffee, and because it affects the supply of coffee, prices are also likely to change due to the supply shock. Now, interesting thing is that when you are doing the regression, as you will see later, it is possible when you have data on prices and rainfall and quantity demanded, it is possible to check whether this correlation is 0 or not. However, it is never actually truly possible to check the or to cross check whether the exogeneity condition holds or not. So, you have to be theoretically sure or theoretically argue whether the exogeneity condition actually holds or not. You have to be confident given the data. In this case, for instance, we have rainfall data, and we have to assume that rainfall does not have a direct impact on demand. As long as you believe that this assumption is likely to hold, you can say that the exogeneity condition is likely to be met, but it has to rest on that assumption. There is no way to actually check whether the correlation between rainfall and U is equal to 0. Okay, so, we can directly check the relevance condition, but not the exogeneity condition. So, once again, just to repeat what I said, the exogeneity condition means that rainfall must not be correlated with U. In other words, rainfall must not be correlated with the error term in the structural equation that we are interested in. So, that rainfall is not, in other words, rainfall is not affecting quantity demanded for coffee directly, but the relevance condition means that rainfall is correlated with the price of coffee. Okay. So, rainfall does affect the quantity demanded for coffee, but only through changes in prices. It does not have a direct impact on the quantity demanded for coffee. So, let us take another example to understand this concept. So, IV in the schooling example. So, when we are talking about the schooling example, what we have in mind is the impact of schooling on earnings, of education on earnings. So, in the estimation of returns to schooling, one popular candidate for Z is the proximity to college or university. So, this was used very famously by Card in his 1995 paper. So, what we are saying over here, remember, is to try to find out whether earnings or wages, however you want to call it, is determined by education. Okay. And the problem is that in the education earnings example, we are talking about a host of omitted variable problems. So, there could be family backgrounds which affect both the education possibilities of a child as well as the earnings possibilities of a child. It could be parental earnings, it could be parental education, and so on. Now, what we need to do, in other words, is to find a variable Z that affects only education, but it does not have an independent impact on earnings. So, one popular candidate for Z is proximity to college or university. Now, does proximity to college or university satisfy the two IV assumptions that we just saw? Does it satisfy A1, which is the exogeneity condition? Well, maybe people who live a long way from a college are more likely to be in low wage labor markets. We could estimate a multiple regression for Y that includes additional regressors such as indicators for non-metropolitan area. So, what this means is that when you take proximity as an IV for education, it is possible that people who live away from a college have lower probability of getting admitted to college simply because they are further away from college or university. However, that is not the only way that affects proximity to college affects earnings. It could be that people who are living away from college are also in low wage labor market. So, the proximity to college does not only reflect your probability of getting educated, it also reflects the kind of labor market you reside in. You might be in a labor market which has lower employment opportunities, it has lower wages, so that proximity to college does not only affect earnings through education, it affects earnings through some other channels. So, this means that proximity to college has a direct effect on earnings through a different labor market. Now, one possibility is that we could still estimate. So, if let us say proximity to college is affecting your earnings through education. Now, it is possible that proximity to college does not affect earnings only through education, but it also affects earnings through the proximity to different labor markets. So, maybe a better or a worse labor market. If you are proximate to college, it might mean that you are in an urban region which does not only have a college, but also has a better labor market with better employment opportunities and higher wages. So, what this means is that if better labor market, proximity to college also implies a better labor market, and that is the only other channel through which you have higher earnings. What you could do is you could control for the fact that you live in a different labor market. Now, after, if let us say there are only two channels through which proximity to college can affect your earnings, one is education, one is a high wage labor market, then controlling for high wage labor market, all you have is the effect of Z, which is proximity, on earnings through education, right. So, this is what it says, that we could still estimate a multiple regression for Y that includes additional regressors such as indicators for non-metropolitan area, which is a proxy for a labor market. But clearly, without controlling for that particular channel through which Z could have also affected earnings, Z is not a valid IV. Now, the second assumption that Z needs to satisfy is the relevance condition. So, does it satisfy the relevance condition? Very likely. People whose homes are a long way from a college or university are less likely to attend college. Once again, remember, you can verify this using the data. However, this exogeneity condition is non-verifiable, something that you have to believe or argue or be sure theoretically that this holds. Another candidate which has been used as an instrument for education is the month of birth of a child combined with compulsory schooling laws. This was used by Angrist and Kruger in 1991. Now, what they are saying is that depending on when a child is born in a particular year, so if you consider two children, one is born in December and one is born in January, and suppose school year starts in January, and suppose the entry age to school is 5 years. So, the child who was born in December of 1990 will actually become 5 years in the December of 1995, but the child who was born in January of 1990 would become 5 years in January of 1995. So, the child who is in January 5 years old can start school in 1995, but the child who was born in the December of 1990 will have to wait one more year to be able to start school. Now, I took two very extreme examples of the first month and the last month of the year when school year is from January to December, but you can also think of any month in between. So, for instance, a person who is born in May as opposed to a person who is born in July, then the child who is born in May is able to start school in a different year than the child who is born in July, depending on when they turn age 5. So, in this case what we are saying is that suppose which is true in the US, they have compulsory schooling laws and these laws vary by the state. So, if you have compulsory schooling law that you have to graduate or you have to attend school for at least let us say 16 years, then depending on when you start schooling, it will decide how many years of schooling you have. So, let us say everyone has wants to drop out of school as soon as they reach 16 years of age, and depending on when they actually start schooling would determine how many years of schooling they had. The child who was born in May of 1990 as opposed to the July of 1990 would have very different number of years of schooling, because they entered school at different times, but by the time they leave school they are both 16 years of age. So, this is exactly what Angrist and Kruger exploit in their paper and say or assume that month of birth is not related to your earnings potential. Month of birth in this case is only determining the extent of education that you achieve combined with the compulsory schooling laws or in the presence of compulsory schooling laws, but it does not have a direct impact on earnings. It only affects education, but does not affect earnings. So, given this possibility that month of birth only affects your years of education, but your month of birth is less likely to affect your earnings directly. There is no theoretical reason, at least a priori when this paper was written, we could not think of any theoretical reasons that a month of birth could affect earnings. To that extent, month of birth is a valid IV, it meets the exogeneity condition. Now, the second one, whether month of birth affects actually your years of education when combined with the minimum school leaving age, which is when combined with the compulsory schooling laws, whether the month of birth affects your extent of education, that we can verify using data. So, once we are able to verify using data whether the relevance condition holds, and if you are willing to believe that the exogeneity condition holds, then we can be sure that Z can be used as an instrumental variable. So, before going further, what we would do is to summarize what we learnt about instrumental variables today, what we learnt in today's lecture. So, the first thing that we discussed is the goal of regression is to estimate the conditional mean function, the expectation of y given x, and when we try to estimate the true value of this expectation of y given x, one way of doing this is the experimental approach, where we try to assign treatment and control to randomly to the units of observation, and this is how we try to retrieve or estimate the true value of the expected conditional mean of expectation y given x. However, this best case scenario of setting up an experiment is not always feasible, particularly in social science research. So, when we are talking about when we are interested in various causal relationships, but it is not always ethically possible, or even when ethically possible, it is not possible financially to set up an experiment to answer all questions causally. Thankfully, in those instances, we have been able to come up, econometricians, statisticians have been able to come up with econometrics or statistical tools that can be utilized to create a condition which is similar to that of experiments, that is, create a counterfactual or construct a counterfactual using the statistical tools and say something about the causal relationship between x and y. Now, there are several such tools that can be utilized, and one of the most prominent ones is instrumental variables that we learned today, or that we started discussing today. And what we discussed is the historical context in which instrumental variables were first used. Now, the historical context in which instrumental variables were first used is the demand supply framework or the simultaneous equation framework, where suppose we are interested in measuring the effect of price changes on quantity demanded. In other words, we are interested in measuring the elasticity of demand or estimating the elasticity of demand. And typically the problem that crops up in such a context is that quantity demanded is not the only dependent variable in the model, in the system of demand and supply, but price itself is determined by quantity demanded and quantity supplied. So, what we have is a system of simultaneous equations where both y and price are outcome variables in different equations, and both y and price are also explanatory variables in different equations. So, where price is an explanatory variable to determine the quantity demanded y is an explanatory variable to determine price of the good in a different equation, where price is the outcome variable. So, in such a context, what we could do is we could use supply shifters that does not affect quantity demanded y, but only affects prices to trace out the demand function. So, what we are saying over here is we have as an instrumental variable or as an instrument a variable that affects prices, which is our explanatory variable when we are interested in the elasticity of demand. So, it affects the prices, the explanatory variable, but does not have an independent effect or a direct effect on y itself. This instrumental variable should affect y only through x and not independently. If this is true or if this holds, if this is valid, then we can retrieve the causal relationship between x and y, from x to y. And we formalized these implicit assumptions or these implicit characteristics of IV in two assumptions that an instrumental variable should meet. The first one is the condition of exogeneity or the exclusion restriction, which is very important for an IV to be valid, which is basically saying that an instrumental variable should be exogenous with respect to the error term u in the structural equation y equal to alpha plus beta x plus u. When it is exogenous means that it is not correlated with u, and another way, another name for this assumption is also the exclusion restriction, meaning that the variable z, which is the instrumental variable, should be excluded from this structural equation. In other words, when you control for x, which is y equal to alpha plus beta x plus u, once you have control for x, z has no role to play in that equation anymore. The second condition that we talked about is the relevance condition, that x and z must be correlated, because only when they are correlated can you have a path, a link from z to x to y, and that helps you to recover the relationship or the true relationship from x to y, even when x and y are or x and u are correlated. So, even when x is actually endogenous, you are able to recover the true relationship from x to y in the presence of a valid instrument, which is where validity means that one, the instrument is excluded from the structural equation, and two, the instrument is a relevant instrument, in other words it is correlated with x. So, with that we end today's discussion, and we would take up further derivations of instrumental variables, various ways of deriving and understanding instrumental variables further in our next class. Thank you for attending today's class. So, until next class.